I have a couple of hints that hopefully will help you to make this not painful. So there's trig functions, which I know are painful, but I've got hints to help the pain. I hope. There's not enough. I'll give you one more. Matthew, enjoy. Here you are. Here, let's see. I'll give some to your friends. I'll make a special delivery. There you are. I think someone's going to have some extras, right? You've got some? Excellent. I'll come get them. All right. Excellent. Thank you. You've got extras? I'll come get it in a minute. Unless you want to do it twice, you can do it twice. Okay, so let's freeze this thing. Oops. All set. Got something? Pretty good to me. Just curious. You double checking? Okay. I don't know why you should double check. Yours look good too.
It's messy, but it's an answer.
It is an answer. Yeah. It could be simplified, but I'm happy for it to not be simplified.
You made it face it.
Well, you may have simplified it different than I did. That's all. Yeah. That's the thing with trig functions. You know, there's no, they don't. They're beautiful. So, wait, what are you doing? Oh, I see what you're doing. That was mean. Ooh, nice box. Big one, big box. No simplification, but that's okay. I'll simplify it for you.
No proof I did that right.
Yeah. What's that? You don't want to simplify?
No proof I did that right.
It could be simplified, but it doesn't have to be. You simplified yours. Very nice. She simplified. He didn't. Got a box. Do you not like your box? Oh, you're double checking. Okay, I'll walk around. It's okay. Double two colors.
Yeah.
Nice. That's all right. Sometimes it helps. Nice. Oh, you're also, now that you have the two colors, you just have to look at the correct color. Very good. Is that it down there? Yes. YP. I see what you did. Just nice. You simplified. Some people chose not to. All right, well, if you're still working, try to wrap things up. Maybe come up with something, label something, and oh, you've got a box, but you just don't want to give it to me? Something like that. Oh, yours is just unsimplified, that's all. He doesn't simplify. So.
You should co-sign over it or just
Well,
both times.
like his is, okay, do I have your permission to show her yours?
Yeah, I'm just gonna keep yours and simplify.
Here, look at how long his answer is. And then here this, and this answer is small. Stuff cancels, yeah. Stuff canceled.
I wrote it at once. I wasn't
Yeah. Well, look at that. So like this guy, yeah, his is super long.
Yeah, 'cause you can get
So
rid of
it's
the sign.
either super long or super short. Some people like the long version. It's fine. You got the long or short? It's almost too short. Yeah, yours would have canceled if you had just written it out. You can multiply out. It's fine. All set? Good. All set? Got something? You did? Oh, look. Oh, wow. Yours is super long. This good? Oh, you've simplified? Oh, he's going to put a box around his. You don't have to simplify if you don't want to. It's all optional. Okay. All right. I think I've got the whole stack. Who's holding out on me? Okay. Stapling, done. Okay, let's see what I did. Hopefully we all have, I think I saw a lot of correct answers and a lot of almost correct answers. So let's see if we got it. First off, I kind of was lazy and I didn't write this part because it was so obvious, but just in case you would do, so this is the very first bit where you say, oh, this is going to be r squared plus 1 is equal to 0. So r is plus or minus I. So the complementary solution is just cosine and sine. Yeah, I guess if you started with something other than cosine and sine, you'd be sunk because the rest of it would be wrong. But there's the beginning. Then you do the Wronskian matrix. So you've got the cosine and sine. Oh, you could have done sine cosine instead of cosine sine, totally fine. It just changes the sign plus or minus, that's it. But anyway, so it would be fine. But I used cosine sine, so the derivatives do the cosine squared minus negative sine squared, which gives you cosine squared plus sine squared, which is 1. So far, so good. So that's nice. If you switch these, it just means that this is -1. It's not a big deal. It would come out in the end. Then we have this business. So what's this? Well, this is, so there's that 1. This is the forcing function, f of x, tangent. And then this is this number, this thing. So it's the f of x times the second piece divided by w. And then that's the derivative. And then that's why, so here I should say something about this, is I will try to not give you hints that are unusable. So for example, I wouldn't do this to you. Like here's some hints, and including that thing, which you're not going to use that. So I'm not going to give you a hint that you're not going to use. So if there's a hint here, it means probably you're going to use it. And here's where I used it. So I'll show you all the hints, but there's this one. So this stuff, the negative of is, I just negated that hint up above. So tangent sine is secant minus cosine. It's a simple trig identity. You can just take this tangent, write it as sine over cosine, and do a little bit of manipulation, and you get this. So I don't want to go into the details, but it's not hard. So anyway, there's that. And then that's that. And then what's U1? Oh, there it is. So I did the antiderivative. Antiderivative of cosine is sine. Antiderivative of secant, I gave you the hint. you should know what the antiderivative of secant is, but you don't, so here it is this. Then where's u2? u2 was easy because it's tangent times cosine. Maybe I should have given you that hint as well, but if you didn't know, tangent is sine over cosine times the cosine. There they go. There. So maybe I should have shown you that hint as well, but I think enough of you got it right that you knew this, so that was easy enough. Then do the antiderivative of sine and you get negative cosine. So now I've got my building blocks. Let's put them all together. So this is my particular solution, a little bit messy. I've got the first piece, the first fundamental solution times this u1. And then I've got the second fundamental solution times u2. The negative there is just for the, the thing. And because, so this is where I was commenting on, like, some people didn't want to have to multiply through and simplify, but you can do cosine times sine minus sine times cosine. They cancel each other, and you get this as your final answer. If you just wrote the particular solution and put a box around it, I'll probably be like, yeah, you're great. I love you. So even though technically this is the correct answer down here, if you simplified it, if you didn't simplify it, it would have more stuff. It would be a little uglier. So I think that's it. Is that okay? Look okay? All right, let's do some, so we started this on Friday in the wind, but we're going to do it for real now, and that is to solve systems of differential equations using elimination. So this is the sort of thing we're going to be doing, is working with systems like this. Now, there is a connection, I should say, between systems of differential equations and high-order differential equations that I'm not showing you, but it's possible to take every high-order differential equation and convert it to a system. Maybe I should show you an example. Yeah, let's do an example real quick. It won't take long. And then I'll get back to how to solve these things. So let's say you have something like this: y double prime plus 2y prime plus y is equal to 0. Let's just make it simple like that. So you might say, well, how in the world am I supposed to take that and turn it into a system of differential equations? Well, here's how you do it. We're gonna assume that that your independent variable is t. I just wanted to point that out because I'm going to use x as a second dependent variable. So here's how I'm going to do this. I'm going to let x equal y prime. That means that x prime is y double prime. And so if you take this stuff and put this stuff in here, here's what happens is you get x. Oh, actually, I don't need to put all of that, just this one. I get x prime plus 2y prime plus y equals 0. And then x minus y prime equals 0. You might say, where'd that second thing come from? Well, it came from right there. So notice that I've taken this second order differential equation and I've converted it into a system of two first order differential equations. So this is just something that we do sometimes to make things easier to solve certain differential equations. So that's the connection and why it is that we're looking at this. Also, because eventually we're going to deal with systems of differential equations that are more complicated than this. But this is a typical system of differential equations. And so to understand how we're going to solve this by elimination, what we need to do is to realize that this thing can be written using the differential operator. And so here's how this is going to look. So let's write this out. Give me a sec. So instead of, here, let's clear that. And actually, this is going to annoy me, so I'm going to have to copy. Give me a sec. Copy. Give you a chance to copy as well. There it is. Okay. Okay, so here's how this works, is we're going to rewrite this. First of all, it would be nice to have all of our variables on the left side, so maybe I'll do that first. X double prime plus 2x prime minus x plus y double prime minus 3y equals 0. That's the first equation. And then the second equation is going to be x prime plus 4x plus y prime minus 2y equals 0. So you see, all I've done is I've just rearranged things so that everything's on the left. By the way, what we're going to do here is we're going to use sort of an algebra technique to solve a differential equation. So if you're not good with algebra, I don't know what to say. But actually, I know that some of you aren't. Well, I shouldn't say it that way. Typically, people who don't do well in like calculus, it's because of algebra. It's not because you don't know your calculus. So you're all really smart. It's just that algebra, for whatever reason, is so hard for people to deal with. So anyway, let's see if we can do this one. So what we'll do is we'll do these one at a time. I'm going to do this one first, and I'm going to rewrite this like this. This is d squared plus 2d minus 1 times x. I'll explain in just a second, plus d squared minus 3 times y. So I think you can probably see what happened here, but just in case, what I did here is I said that this thing, x double prime, it's the second derivative of x. So I could rewrite this or re-represent this as this, having two d's, so d times d, where d represents the differential operator. You're operating on the function x. Second derivative is d squared because you're doing the second derivative. D to the first power is going to be the first derivative, and then the 1 there just represents the little x there. So this is sort of reminiscent of when you were doing your characteristic equation, having r's and replacing all of the double primes with r squared and all the single primes with r. Here, though, this is literally an operator where, like the derivative, the Lebesgue derivative, or Laplace, which is it, Lebesgue or Laplace? Lebesgue derivative representation, the dy over dx, that's operator notation. So this is an operator as well. So I've done that. I'll do the same thing down below. And then it's a simple job of, well, simple in quotes, of solving an algebra equation. So this is d plus 4 times x, and this is d minus 2 times y. We'll come back to this maybe, but this is a hard one to do. I know I say it's simple, but it's the sense is that we have to do algebra to eliminate one of these variables. But in doing so, we're going to make a more complicated differential equation. So let's go back to PowerPoint land just for a moment and pick a simpler differential equation. So this system has just two first order differential equations. And notice I've written this two different ways. On the left, you have it written the way you would write a system of differential equations, and on the left. And then on the right, I have it in operator notation with the D. And I've moved all of the letters over to the left. Typically, when we write a system out like that on the left, we do it with the derivatives equal and then whatever function of y and x on the right. That's just typical of the way things happen. And so we'll have some applications, I guess, that you'll see will look like that eventually. But on the right is the way that we're going to use to solve this. So let's go, and I will do this right here. Give me a sec. There. So there's the two things. Take a minute, look those over, and then we'll see how we're going to work with this. So this is the technique. Even though you guys love substitution, we're going to use elimination for this. So every one of these differential equations. So what you want to do is think algebraically. Think in terms of the algebra that you need to do. How do I manipulate these two so that I can eventually eliminate one of the variables? And I don't care which variable you eliminate. So take a minute, see if you can figure out how to rearrange these, and just think of the capital D as a number, like 7 or whatever. So don't think of it as being something special. Just let's treat it the way you would the number 3. I'm gonna check my attendance, and then I'll be able to pick someone. Very good. Okay, let's see how we're doing. I know you're all on the board with this, but Cooper asks, what are you going to do? Like, how do you want to manipulate these? What do you want to eliminate? The x's. So if you're going to eliminate the x's, what are we going to have to multiply the top thing by? 2, very good. So let me do that. And then Matthew's going to tell us what to multiply the bottom thing by. So 2dx minus 6y is equal to 0. So you see what Cooper did there is he's got this multiplied by 2. And then Matthew, what would you like to multiply this by so that it has the same coefficient? You want to do a negative? Okay. So we'll multiply, here, I'll write this up here. We're going to multiply this times 2, this times negative, and what else do you need to multiply by to make the coefficient of x the same as this? The d, yeah, very good. So multiply by negative d. So we'll do that. And so this is negative 2d x plus 2d, oh no, there's no 2. D squared y. Double check my work here, or Matthew's work. We'll blame him if there's something wrong. Actually, you probably should blame me because I'm the one who wrote it here and I probably copied something incorrectly. Does it look okay? So let's just go ahead and blindly, at least for now, we'll just say, okay, let's give it a go, naively add these together, see if it works. And it does. That's the beauty of this method, is it will work. So add these together, we have 0x, and then d squared minus 6 times y equals 0. So what we've done here is we've rearranged these two differential equations in such a way that allows us to eliminate one of the variables, and then we will work on the other variable. By the way that the book suggests that you do this is they want you to do this twice, do the exact same thing, but eliminate the y variable next. So we're going to do it that way, even though it's not entirely necessary. It's possible to do this. Let's see, how can I copy? Copy? Is this copy? Oh, there, duplicate. Good enough. Okay, so I'm going to just move this down here so that we have room, and we will do it again. So we're basically going to do the exact same thing that we just did, but instead of eliminating the x's, we'll eliminate the y's in just a bit. So that's in our future. For now, let's take a look at what we're left with. We're left with d squared y, that's y double prime, minus 6y is equal to 0. I'll bet that you can come up with the solution to that. Take a minute and see if you can do it. And I'll make some room here. There we go. Find a volunteer. Let's see where we're at. Joshua, what did you do to, do you have a solution, or are you doing like, what's your technique here? Oh, linear. Okay. Well, what do you mean by that? Oh, let's not do that. This is a second order differential equation. I mean, you probably could, but I don't want to do that. Let's do the whole r squared thing. Yeah, second. So let's, what is it? R squared? Oh, yeah. Okay, you're getting ahead. I mean, yeah, perfect. So r squared minus 6 equals 0. You remember doing this with second order differential equations. So r is plus or minus square root of 6. Very good. So that's the characteristic equation. Sometimes we call those characteristic roots. Zechariah, do you know what we do with those plus or minus radical 6s? And don't forget a t. You got to have a t in there somewhere. But yeah, that's perfect. Very nice. So there's my general solution for y if the x didn't exist. Well, now we're going to do the same thing down here. I just want to point out something about this, though, before I do this next step. And that is that it is possible to take what we have here, shove it into like what we do when we're doing elimination back in algebra class in 8th grade, is you would take the answer for y, stick it back in, and then you get an answer for x. And certainly, I mean, look at this. This particular line here would have been really easy. You just do the derivative of y is equal to 2x. So that would probably be the easiest thing, but I'm going to do it the way the book does it. And so it's not going to be too much more work at this point. So let's go ahead and do this. And actually, saying that you can do that every single time is true, but in this case, it's easy. It's not always as easy as I'm making it out to be. So yes, so I'll stay with the program. So let's do the same thing. And now instead of eliminating the x term, I want to eliminate the y. So we need to figure out, what do I multiply by in each of these cases to eliminate the y. So let's find a couple of things. Rachel J., what do you want to multiply the top line by? All right, let's do that. Negative d. All right, and if we do that, then we're going to have to, oh, you're not here, but you know it. Let's try, how about Adric? You know it too. Adric, what do you want to multiply the bottom by? Yeah, so just positive 3. That way, one of these will be negative, one of them will be positive. So we have negative d squared x minus or plus 3dy. And then on the bottom, I've got 6x minus 3dy. Did I get all that right? And then let's go ahead and stick this down here. So negative 6d. Sorry, I multiplied instead of added. Negative d squared plus 6 times x is equal to 0. Is that right? I think it is. So something that may be somewhat surprising happens, and that is that you end up with x double prime minus 6x equals 0. You zoom out. I don't know if you notice the relationship with what's written right at the top. But I mean, I should say I negated after, it's really negative x double prime plus 6x, but I just wanted it to look like what's up there at the top. So I'll bet we can figure this one out without doing any extra work. All right, Claire, do you know what the general solution is for x? All right, so my only problem with the way that you said that is that C1, yeah, so C1 is this up here, and C2 is this one up here. So we really need to have a C3 and a C4. What a pain. Well, now we're going to actually, once again, this is one of the costs of doing it this way, but here we are. Give me a sec. Copy this. Why is this not moving? Just a sec. Hold on a minute. Copy. Okay, there it is. Move this down, and then this is the last time I'm going to use this. Okay, so here's what I've got. Is I've got my x, and I'm going to copy the y from up above. C1 e to the negative 6t plus C2 e to the 6t, radical. There it is. So 4 different unknowns, 4 different constants, but there are relationships that exist between all those constants. So here's the unfortunate thing that we're going to have to deal with, and that is we need to figure out what is the relationship between C1, C2, C3, and C4. So this could have been avoided. I just want to point out something. If instead of doing it like the book did it, which the book, it's going to sound like I don't like the way the book did it. I only don't like the way the book does it for simple problems like this. With harder problems, it is far easier to do what we're about to do. But in this case, I could have taken this and stuck it in here and solved for that x right there. And you would have gotten the correct answer. So just so you know, there is a slightly easier way with this one problem, but it's not always this easy. So let's go ahead and crank through. What I'm going to do is I'm going to take these two and I'm going to stick them into, well, either this or this. They're basically the same thing. And then I'm going to solve for C1 and C2. So pick one. I don't care which. I'm going to use this one just to show you how it works. I need the derivative of x with respect to t. So the derivative of x with respect to t is negative radical 6 c3 e to the negative radical 6 t plus radical 6 c4 e to the radical 6 t. Oops, why am I putting a plus there? I don't know. Okay, so that there, this is this. Okay, on the other side, I'm going to put 3y, so 3c1 e to the negative radical 6t plus 3c2 e to the radical 6t. So it's not that big of a deal, I guess, because now you can see, hopefully you can see the relationship between C1, C2, C3, and C4. If you can't see it quite yet, I will make it hopefully somewhat more obvious. And that is that C1, let's do C1, this thing is the part of the function with the negative radical 6t. That corresponds with this thing. So these two should correspond with one another, which means that negative radical 6 C3 should equal 3 C1. Or in other words, you have C3 is 3, while negative 3 over radical 6 C1. So far, so good? See if you can use a similar reasoning to figure out the relationship between C4 and C2. Probably not that hard to see that that's going to be this radical 6c4 is 3c2, because these are the part of the function that corresponds with the e to the radical 6t. So those have to line up, which means that c4 is 3 over radical 6 c2. And I know it's probably bothering some of you that I'm actually, making the radical in the denominator. If you prefer, you can write these like this: negative radical 6 over 2, and C4 is radical 6 over 2, sorry, C1, C2. Just do a little bit of, basically just multiply top and bottom of each of these by radical 6, and it'll end up making it 3 over 6 times radical 6, which is radical 6 over 2. So anyway, however you cut it, what's going to happen is that my final answer, let's see if I can get my final answer. Whoops. Nope. Sorry, I'm trying to copy so I don't have to write. Good enough? Okay, so my final answer is just where I've replaced those C3s and the C4 with what I have here. So C3 was negative radical 6 over 2 C1, and C4 is radical 6 over 2 C2. So there's the final answer. Now, I think you can probably guess that this gets kind of nasty pretty quickly, because that was a lot of work for what looks like a pretty simple set of differential equations up there. Eventually, we will learn techniques to solve systems of differential equations that will be easier or different. I shouldn't say easier. They'll rely on linear algebra. which, you know, I guess you're out of the fire or out of the frying pan into the fire maybe. But, eigenvalue, eigenvectors. It's, if you've ever wondered what are these things useful for, differential equations, eigenvalue, eigenvectors. I always thought they were garbage until I took differential equations. I was like, oh, this is useful. It's actually really interesting. But we'll get to that later on. For now, let's go take a look at another example and see what we have. Let's see, that one's done. Let's see, pick one that's not too bad. Let's try this one. We'll see how it goes. So try this. And then I don't think, sadly, or maybe I should be happy about it. We're not going to have time for the first one that we had, which was kind of ugly. So that's probably good. Okay, good. Done. Copy. Why won't it copy? Okay, there. Okay, give me a sec. I'm going to put this over on Notability so I don't have to try to cram everything on there. No, delete. There we go. Wow, good enough. All right, let's give it a go here. So we're going to use elimination. So let's just do it the way we did last time. We're going to systematically eliminate each of these variables. So start by eliminating the x variable. So you're going to have to figure out what are you going to multiply by to line up the two things. And then we're going to eliminate the y variable after that. So we're just going to have to do this twice. So might as well just get this started for the y variable. All right, so here, let's get her going. You're not here. Andrew's here though. Andrew, what do I multiply the top by to get rid of the x variable? So you want these things to line up and they don't. So you want to make sort of the same thing. So I could multiply this by something and multiply this by something. Very good. So we're going to multiply the top by d minus 3. All right, Mariah, what about the bottom? What do I multiply that by? Yeah, d or negative d, however you want it, depending on if you want to have them line up exactly or if you want one to be the negative of the other. So then I get d minus 3 times d times x plus d minus 3 times d plus 2 times y. And I think you probably can appreciate why this gets kind of ugly pretty quickly. D minus 3 times x, and this is going to be negative, plus d times y. Now, if you've been careful and done this correctly, the x's will line up and they will cancel. That's the whole point of elimination. And so we're left with just d minus 3 times d plus 2 times y plus 2dy. Thank you. Yeah, that would have been disastrous. Let me expand this for you before we actually solve this. So d squared minus minus 6 times y plus 2dy. So that gives you y double prime plus y prime minus 6y equals 0. So there it is. That's the differential equation after. The reason why it's plus 6 is you've got minus the derivative plus 2 times the derivative. So that's why I have that. So see if you can get your general solution of that. And then we'll talk about the second piece. All right, well, I've left some blanks here for you to fill in. And if we need to, we could write down the characteristic equation over here, but I think you probably can almost do it without writing it down. Rachel P., did you get your 2 fundamental solutions for this? Beautiful. Nice. Okay, so there you go. So now we're going to do the same thing, but now we're going to eliminate the y instead of eliminating the x. So let's see if we can do that. Madison, what am I going to multiply these things by to eliminate the y? So you want this and this to cancel. So like up here, you multiplied the bottom by d and the top by d minus 3. D plus 2, you say? Okay, so multiply the bottom by d plus 2. Or just 2, you said? Because there's just a 2 here. That way the things will line up. All right, yeah, that's exactly right. So you take the coefficient of y down here and multiply that by the top, and the coefficient of y up here and multiply that by on the bottom. Okay, so this will be 2dx plus 2 times d plus 2 times y is equal to 0. And then this will be d plus 2 times d minus 3 times x minus 2 times d plus 2 times y. Whew. Subtract or just add those together. So this will be d squared minus d plus 6 times x plus 2dx. And lo and behold, we end up with exactly the same, exactly the same differential equation, only with x's instead of, wait, that should be a minus, shouldn't it? Minus 6x. So the same differential equation. It doesn't always work out that it's exactly the same, but in these cases that we've been doing it, it is the same. So that's sort of confirmation that we're on the right track. So x ends up being C3 times e to the negative. I'm just going to do the work, use the work that you guys did above. 3t plus C4 e to the 2t. Okay, so your final step is to figure out the relationship between C1, C2, C3, and C4. So give me a sec. I will copy that. Sure. Move this down just so that you have room, or I have room. And you can use either of these differential equations, doesn't matter which. So you pick one, pick the one you like the best, and that's the one we'll use. So whichever one looks like it'll be the least amount of work probably would be best. I have my opinion, but you might have your own. Tyler, do you have an opinion about which of these 2 you want to use? Yeah, bottom one feels good. Top one you could do if you're, a glutton for punishment. Go ahead and do it. It just means more work, not a whole bunch more, but this one, what probably is catching Tyler's eye, what catches my eye is I don't have to do a derivative for y because it's just 2 times y. I have to do a derivative for x. That's what that d means. Do the derivative, but the 2y, I'm not going to have to mess with the y. So here I'm going to be sort of, well, not lazy, but just efficient. And I'm going to paste this down here. There it is. So that's my y. Hold on a minute. So there's 2 times that. And then I need x. So there's my x. Bear with me. I'm going to just go ahead and do the derivative to make things a little bit more efficient. Let's see, move this over a little bit more. Whoa, it's all moving. Okay, good. So let's see. 3 times x. Let's see, this will be a negative. Whoops. This will be a negative because of that negative. So I'm kind of working my way backwards. I have C3 e to the negative 3t plus C4 e to the 2t. And that's going to be 3 times that. And then I've got to do the derivative of all that. So let's see, the derivative of all of that is the derivative of this. That'll be negative 3c3 e to the negative 3t plus 2c4 e to the 2t. Okay, so just in case you're curious, like where did everything go? This is the derivative of x. And this is just the x, I guess 3x there. Now it's really hard to read, so I'm going to erase my highlighting. Okay, let's collect all the like terms. And then we got to get out of here because it's what, 3:04 already? My goodness, we got to go do something else. Okay, so let's see. What I'll do is I will collect all of the e to the 3t's. So e to the negative 3t. And then I'll collect all the e to the 2t's over here. Okay, so e to the negative 3t. So I've got negative 3c3, and I'll check them off when I do them. There's another negative 3c3. That's that one. And then there is a negative 2c1, and that's that one. Did I get all the e to the negative 3t's? Now I'm going to do the same thing for the e to the 2t. I have 2c4, that's this one, and then minus 3c4, that's this one. And I know it looks like it's just plus c4, but you have to remember, multiply through, and then minus 2c2. I think I got all of those. Now the key here is that both of these have to equal 0. And the only way for everything to equal 0 is because you have these functions, and those functions are linearly independent, each of those coefficients have to equal 0. So what we'll do is we'll just set this up like this. Let's see, we'll take this one first. That thing, because that one's going to be easier, negative c4 minus 2c2 is equal to 0, which means that c4 is negative 2c2. So c4 is negative 2c2. And then this one, that gives me negative 6c3, c3, minus 2c1 is equal to 0. So that means c3 is equal to negative 1/3 c1. Does that work out? Sadly, I've got a fraction. I know, annoying. I suppose you could say, well, why don't you just let c1 equal 3c3? You could do that. That would be fine. But I'm going to do it this way because I think this is the way the book would do it. And then my final answer is to have my y. Where is my y? There it is. Hold on a minute. Here's my y. Copy, paste this down here. And my x, that's this one right here. Copy and paste. And I'm going to put in, so there, I'm not quite done. Let's just change the c's. So instead of c3, I have negative 1/3 c1. And instead of c4, I have negative 2 c2. Surely I could clean this up a little bit more, but I'm happy with it the way it is. So there you have it, system. Whew. All right, so give it a go. See how things go for Wednesday. Hopefully they won't be too terrible. I'm going to stop the recording in case you want to come whisper something.